Hello everyone. Today we will be talking about this concept of splay trees. So, have you ever wondered if there's a way to automatically organize data so that most frequently accessed items are the easiest to reach? Today we're diving into the world of splay trees, a fascinating type of binary search tree that does just that. So, splay trees are self adjusting binary search trees that bring recently accessed elements closer to the root, making future accesses to those elements faster. Let's explore how they work, their operations, and where they can be incredibly useful. So, this concept actually has the same property as BST, or commonly known as a binary search tree. So before we dive into this, we'll actually get a brief recap on what a binary search tree is. So in a BST, each node has a key greater than all the keys in its left subtree and less than those in its right subtree. This property allows for quick data retrieval, insertion, and deletion. So now we can kind of go to this transition to splay trees. While BSTs are efficient, they can become unbalanced with frequent updates. Here's where splay trees shine by keeping themselves well balanced without explicit rules or balance factors. Okay, so why should we use this splay concept? So the idea actually of this of splaying is to bring the most commonly used element to the root of the tree, which can reduce search time as mentioned. So before we kind of dive into examples and this idea of this concept, we'll actually look over at this runtime complexity. So for insertion, deletion, and searching, the worst case scenario would be big O of n. But this is not the case when you actually use this data structure more. The amortized time actually ends up being O log of n with a space complexity of O of n. So this is simple for just the storage of the tree. So this each time a node is moved during this splaying, it is called a splay operation. Okay, so let's kind of dive deep into these three different types of splay operation. So we'll start off with this idea of zig. So this is when a single rotation is when the node is a child of the root. So as you can see here, we have this X node, and this X node is what we want to actually splay to the root. So as you can see in this zig scenario, X actually gets moved into the root, and then Y gets placed into the left subtree where it's still holding this binary search tree properties. Okay, and now there's the case of zig zig. So this is actually the double rotation when the node and its parent is on the same side of their respective parent. So as we can see in this case, we want to move X and do the splay operation with this node. So what happens is it does this double rotation where now the tree gets restructured like so, and then it gets restructured into this. So now X ends up being the root. Okay, now let's look at the third case where it's called zigzag. So this is also a double rotation when the node and its parents on different sides. So it's called zigzag because as you can see, kind of the formation of it ends up being a zigzag. So upon the first rotation, it actually moves the X value, which is what we're looking for, into this formation. And then upon moving it to the root, it ends up taking this formation as well. So it's constantly changing this kind of structure of how the tree is. So now let's ask, when should we use this splay operation or this concept of splaying? So upon inserting, when we're inserting a new node, that node will automatically get splayed to the root. So whenever there's a node that gets implemented, it gets pushed to the root after it is done. So now let's talk about deletion. When a node is deleted, that node parents get splayed to the root as well. So When we remove that node, we have to find whatever the parent is, and that gets pushed back to the top of the root. And now, lastly, searching. So now searching is kind of this more complex factor, but yet again, it's fairly simple. So if the key for that particular node is found, that node containing the key will actually be splayed to the root. But sometimes it may not always be the case where you are searching for a key and it exists in the binary tree. So if the key is not found, then we end up splaying the parent of the left position where you try to find that key at. So that's kind of this overall concept of splaying and when we can kind of use it. But now let's kind of like talk a little bit about its benefits and drawbacks. So, if we're talking about the idea of adaptiveness, one of the greatest advantages of the splay tree is the adaptiveness. Frequently accessed nodes stay near to the root, making them quicker to access over time. This actually gets really useful in the real world scenario. And now, more detail about this amortized complexity we talked about. While each operation can potentially, right, a worst case scenario, take big O of n time, the amortized complexity becomes O log of n for a series of operations thanks to this self-adjusting nature of the display tree. However, obviously there's got to be some drawbacks to these type of data structures or concepts. The need to splay on every operation can make splay trees slower in scenarios where the tree needs to remain relatively statistic. So, also for splay trees, there's a lot of use cases for it. So these ideal for applications with non-uniform access patterns, such as implementing caches, data compression algorithms, or certain type of memory management schemes. So, in conclusion, for splay trees, they're a very great dynamic solution for maintaining an efficient order within a binary search tree, especially when some elements are accessed more frequently than others.